So uniform circular motion, what that means is we've got an object that's traveling around in a circle, and not a terrible circle that I've drawn, but of course not perfect, but we'll pretend that everywhere the radius is some constant value. We'll call it r, and whatever this little thing is, it's going around in a circle like that. But before we talk about this, I want to talk a little bit about acceleration. So acceleration is the rate of change of velocity with respect to time, the derivative of velocity with respect to time. And it turns out you can have a situation where the acceleration is not zero, but the velocity has a magnitude which doesn't change, or it's constant. It seems like maybe that should be impossible, because of course if acceleration isn't zero, that means the velocity is changing, but if the speed is constant, that must mean the direction is changing. And that's what's going on here with uniform circular motion. Not only are we moving in a circle, so a uniform distance from the center, but we're also doing so at a constant speed. And that means that the acceleration and the velocity have got to be perpendicular to each other. And we draw that with this little figure right here. So this means that acceleration and velocity are perpendicular, or at 90 degrees to each other. So to see why that causes the circle, I'll say you've got velocity this way and you have acceleration that way. They're at 90 degrees to each other. Acceleration is the change in velocity, so acceleration is going this way. Velocity's got to be going that way, and so that means a moment later, the velocity is going to have turned by as much as the acceleration says it has to. So a little bit later, the velocity would actually be going in that direction. But then if we keep having acceleration perpendicular to velocity, then acceleration must still be perpendicular to velocity. So if velocity is this way, acceleration's got to be at a right angle that way, and now velocity needs to change direction again. So instead of going like this, it's now turned with the acceleration. It's going like that now. And then acceleration's still got to be perpendicular. So it has also changed direction. So this kind of motion where acceleration and velocity remain perpendicular to each other the whole time is what causes this uniform circular motion. And that means that we can, we always know the relative directions of acceleration and velocity, but we can also come up with some equations. So if we have a situation like this, we call this acceleration centripetal acceleration. And centripetal stands for it's center seeking. So if you take this small chunk of the circle, you can see the acceleration is always going to be pointing into the middle or the center of the circle. So that's where it gets its name. And it is equal to the speed squared divided by the radius of the circle. Now let's double check to make sure those units make sense. Acceleration, it's going to have units of meters per second squared. Velocity, of course, has units of meters over seconds, and then that whole quantity is squared because velocity is squared. And then radius, that's a distance, it's got unit of meters. So we'll square the meters on top, meters squared, square the seconds, and the meters on the bottom from the radius just stay as they are. But then that is meters over seconds, meters squared over seconds squared, and we are dividing by this, but we've got fractions and fractions, so let's multiply by the reciprocal of meters, which is 1 over meters, and one of those meters cancel, and we end up with meters over seconds squared, which is what we should have. So whenever you meet a new equation, always good to work through the units and make sure you understand that the units are working out okay. The other thing to do when you first get to a new equation is say, okay, if I make velocity bigger, the speed bigger, what's going to happen to the acceleration? In this case, I'm making the number on the top of the fraction a bigger number. And that means the result is going to be bigger. So speed goes up, acceleration goes up. And then radius. If I make the radius bigger, what's going to happen to the acceleration? Well, if radius gets bigger, we're dividing the speed by a bigger number, and that's going to result in a smaller number. We're dividing it by a larger quantity, so the result will be smaller. So radius goes up, centripetal acceleration will go down. The final thing that's useful to know about uniform circular motion is how long it takes it to get around the circle. So that's the period of revolution, and we use the symbol T for that. And that is, of course, going to be, well, the faster we're going, the greater our speed, the less time it should take us to get around the circle. So we're dividing by v there. And then I guess this is time. So we can think of this as velocity is distance over time. So we rearrange it to find time, which is what we're doing here, will be distance divided by velocity. So we need to figure out what the distance is that goes up here. Just using velocity as distance over time, rearranging to solve for time. This is a time, a period, divided by our velocity. And the distance is going to be all the way around the circle, or the circumference of the circle, which is 2 pi r. And we can make sure this makes sense. If the radius is bigger, that is, we've got a bigger circle, r will be bigger, so the period will be bigger. It will take us a longer time to go around a bigger circle. Makes sense? If our velocity is bigger, and therefore our speed is larger, has a bigger magnitude velocity does, then this number will be bigger. We'll be dividing by a bigger number, and that's going to make the time smaller. And that also makes sense. If we're going faster, it'll take us less time to go around the circle. So this will get you started on uniform circular motion.